Imagine you are observing the black night sky with a telescope and everything you see are enormous stars and planets. But wait, what is this strange periodic blinking object? Is it someone playing tricks on you? Is it a star which got into the mood of dancing? Or is it some alien civilization trying to communicate? This was the speculation on August 6, 1967, when Jocelyn Bell discovered the very first pulsar using a radio telescope. They doubted that it might be from an alien source, so they nicknamed the signal LGM-1 or Little Green Men.
And I switched on the high-speed recorder and it came blip, 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 blip. Clearly the same family, the same sort of stuff. And that was great. That was really sweet. It finally scotched the little green men hypothesis, because it's highly unlikely there's two lots of little green men, opposite sides of the universe, both deciding to signal to a rather inconspicuous planet Earth at the same time, using a daft technique and a rather commonplace frequency.
Well, let's then listen to the biography of Pulsar.
Stars exist because of a fragile balance. The mass of billions of trillions of tons of hot plasma is being pulled inwards by gravity and squeezed together with so much force that nuclei of elements fuse to form new elements. This releases energy which pushes against the gravity. As long as this balance exists, stars are pretty stable. Eventually, after millions and billions of years, the star will exhaust its nuclear fuel. Then the gravitational pressure will win over the radiation pressure. When that happens, stars like our sun will swell up, engulfing the inner planets and becoming a red giant. After millions of years, the red giant will turn into a white dwarf that leaves behind colorful stellar arcs called planetary nebula. For the stars around 10 times heavier than the sun, the events are more exciting and dramatic. The balance tips in favor of gravity, squeezing the star tighter and tighter. The core burns hotter and faster, while the outer layers of the star swell hundreds of times, fusing heavier and heavier elements. Carbon burns to neon in centuries, neon to oxygen in a year, oxygen to silicon in months, and silicon to iron in days. Fusion of higher elements cannot happen anymore. Without the outward pressure from fusion, the core is crushed by the enormous weight of the star above it. Due to enormous pressure, the atomic nuclei collapse. Electrons leave their quantum orbits and fall into the nuclei, combining with protons to form neutrons, which then get squeezed together as tightly as in atomic nuclei. At such high densities, neutrons begin to experience a strong repulsive force because of the Pauli exclusion principle. This tries to balance the pressure from the enormous mass. The iron core, the size of the Earth, collapses to the city of the size of Kolkata, tens of kilometers, at 1/4 the speed of light. The core bounces and sends shock waves outside into the involving material and catapults the rest of the star into space. This results in the supernova explosion, and it outshines entire galaxies.
We all know that when a rotating ballet dancer pulls her arms closer, she spins more rapidly. This is due to the conservation of angular momentum. Due to the very same reason, when a rotating star that is typically millions of kilometers broad collapses into a neutron star of around 25 km wide, they spin much more rapidly than the parent star. The interior of a neutron star contains a powerful electrical current of plasma. In analogy with the electromagnets, they generate a huge amount of magnetic field. This giant rapidly spinning electromagnet produces an electric field that accelerates electrons and protons on the surface and creates an electromagnetic field emanating from the magnetic poles. This forms vortexes at the magnetic poles. Thus, after a series of events, we form a pulsating radio source that emits electromagnetic beams at the magnetic poles called pulsars. These vortices are usually not aligned with the rotation axis of the pulsar. Thus, rotating pulsars shine light periodically on the observers sitting on Earth, which causes the blinking of pulsars, the same as a lighthouse throws light on the sailing ship. For now, over 2,000 pulsars have been detected in total. Scientists discovered pulsars by using telescopes of all wavelengths, and radio remains the primary means of hunting these objects. The telescopes can scan the entire sky, and over time we can look for objects that flicker in and out of view. Most of the pulsars rotate on the order of once per second, called slow pulsars, while more than 200 pulsars that rotate hundreds of times per second are called millisecond pulsars. The fastest known millisecond pulsars can rotate more than 700 times per second.
These pulsars do eventually slow down as they age. Pulsars that slow down lose power and gradually stop emitting radiation. When pulsars reach this stage of life, they die and enter pulsar graveyard. However, they can wake up once more. When a pulsar is situated near a stellar companion, it can siphon material and energy from its neighbor. This increases its spin to hundreds of times per second, thus creating a millisecond pulsar. These cannibalistic pulsars are called redback pulsars or black widow pulsars, named after species of spiders known to kill their partners. Now let's dive deeper into the pulsars and explore their interiors. Since pulsars are spinning neutron stars, so to understand their internal structure, we will study the anatomy of the neutron stars. Pulsars have an atmosphere, envelope, outer and inner crust and core. The atmosphere of a neutron star is only about 4 inches thick, has enormous density and pressure. The temperature is estimated to be almost 2 million degrees. Below the atmosphere, there is a thin heat blanketing envelope that produces substantial thermal insulation of warm neutron star interiors, which relates the star's internal temperature to its effective surface temperature, having a temperature gradient of 10 to the power 6 to 10 to the power 8 Kelvin. Below the envelope, one encounters a solid crust. The outer crust consists of a lattice of iron 56. The atoms are fully ionized owing to the high density. As we move inwards, the density increases, and at densities above 10 to the power 7 gram per centimeter cube, the composition of the nuclei becomes more neutron rich as all the electrons collapse into the nuclei. The inner crust, which has a high density, is characterized by the presence of free neutrons, which may condense into a superfluid phase in some. At the bottom of the crust, the stable nuclear shape changes from spheres to spirals like fusilli or cylinders like spaghetti or even flat slabs like lasagna. The strange form of matter inside neutron stars forms the so-called nuclear pasta. The neutron star's core remains unexplored due to limits of theoretical modeling and quantum physics at such an extreme temperature and pressure.
The discovery of pulsars allowed astronomers to study an object never observed before, the neutron star. These cosmic tools are the only laboratory of supercondensed matter. Pulsar maps have been included on the 2 Pioneer plaques as well as the Voyager Golden Record. They show the position of the Sun relative to 14 pulsars, which are identified by the unique timing of their electromagnetic pulses, so that potential LGMs can calculate our position both in space and time. Because pulsars are emitting very regular pulses of radio waves, their radio transmissions do not require daily corrections. Pulsars are used to test aspects of Einstein's theory of relativity, such as the universal force of gravity. Thus, a series of stellar events conspired to form giant ballet dancers in the night sky. They form the laboratory of strange matter physics and serve as the best cosmic tools to study numerous stellar phenomena, as well as keep our clocks synchronized with our LGM brothers.